Good afternoon. It's a pleasure to be here. Everything seems to be falling apart right away. Yes, my name is John Wen. I've been involved with ROS Industrial and also ARM, advanced robotics in manufacturing. And Joe will be talking about ARM next, so I want to give him a plug. And we've been involved in both organizations for multiple years, since 2016 or so for the proposal for ARM, and then 2017 for the founding of ARM. So we certainly have been using a lot of open source software and the tools resulting from the open source community. For example, MoveIt, we use MoveIt. We use, of course, OpenCV. We use Tesseract. Not all of our projects are based in ROS. However, in almost all the projects, we draw on some pieces of open source software. So I just want to encourage those who are thinking about ROS Industrial. You can benefit from a ROS Industrial consortium, even if you don't use ROS, because those are a whole slew of algorithms, and they have been vetted by the community to a certain extent. Otherwise, you have this smorgasbord of thousands of packages. Which one do you really use? I think ROS Industrial provides a nice community to provide input on which one to choose. And I neglected to include any slides about RPI. Probably not all of you know about RPI. My dean would probably not be happy that I don't have any slides plugging about RPI. Just wanted to say RPI is the oldest civilian engineering school in the United States. You may or may not know. So next year is our 200th anniversary. My new president, Marty Schmidt, who was the provost at MIT. He just became the president about a year ago of RPI. He graduated from our department in 1981, and he's now a faculty in my department. So technically, I'm his boss, but I usually don't push that point. But he's a very strong supporter, and he said there will be a big party, so everybody's welcome to come to lovely Troy, New York, upstate New York. The party probably will not be in December, but should be next year. This time should be a lot of fun. Okay, so the quick agenda. So we looked at so GE brought this case, this use case to us. I'll be talking about their use case in a minute. So when we initially looked at it, we said, oh, this got to be a solved problem, right? And we talked to other people say, oh, this got to be a solved problem. You just use RoboDK, right? You use Robot Master, use Octopus, done, right? If you can do this, in CNC, bunch of G code, you're done, right? We say, oh, okay. So we went back to look at the problem a little closer, peel back and say, wait a minute, there's still a lot of heuristics and a lot of manual tuning that's done right now. And there's no idea how optimal or how near optimal, whether there's room for improvement or not, right? And also it takes a lot of engineering time to tweak it to work. So we developed new method thanks to ARM support. And we have demonstration results. We do software implementation, and this is in partnership with GE, with Swarry. We use Tesseract for a number of different things, and Watson technology. And then I'll talk about some path beyond this project. Oh, okay, I do have some this slides. Wonderful. This is RPI. Okay, this is us. And this is, so we have long history of working with industry in robotics automation manufacturing, with strong support in New York State. We have a strong education program in manufacturing, work with all our partners. So that's my obligatory plug for RPI. So now, so the motivation for this project is for cold spray. And this is a turbine blade, and so this is a cold spray coating, which is the high-speed impingement of particle on the blade on the leading edge to give it additional strength and corrosion resistance. And this is from YouTube, and you see, oh, it's not just one robot, but it's two Fanuc robots working together, using something called coordinate motion, which you have to purchase extra from Fanuc. And you say, oh God, this is like really weird motion. How the heck do you teach the waypoints, right, for the robots? So, but they did it, and then they say, so they did it, first of all, for a single robot, And then when they push for 2 robots, things get a little dicey. Okay, why is that? Okay, because you have the task itself is 5 degrees of freedom. You have the 3 degrees of freedom position and 2 degrees of freedom of orientation because you can roll, right? And then, so you have 1 degree redundancy for a 6-stop robot. Now for 12, so now 2 robots, 12 stops, you have 7 degrees redundancy. How do you resolve that 7 degrees redundancy, right? It's by hand. Furthermore, the requirement, this is maybe just GE, right? So it's not universal, so lots of applications doesn't require. They need high accuracy to be, because for the cold spray to really produce the impact that you need to be very close. So they say plus minus 0.5 millimeter, 3 degree normal. And they want very high speed. When they came to us, they say our reach goal is 5 meters per second. I said, well, why don't we dial it back a little bit? So I said, let's make it greater than 1. Okay, even that is not easy, right? And then furthermore, they want this to be uniform speed, right? To have as uniform coding as possible. So what is it done right now? How do they do it right now? So first of all, let's consider single arm with a fixed part. So you have a single, so this is in our lab, we have ABB robot 6640, and with another robot just fixed, so holding apart. So these are two test fixtures we have. So the first part is you need to determine where to put the part with respect to the robot, right? Okay, that's position orientation. And you can put it on a stand, and then so that's a number of degrees of freedom. And then determine the tool orientation, because you have 5 degrees of freedom, so you need to determine this additional degree of freedom. And then you have to choose the arm post. This is a kind of a little subtle point because, earlier Dave Coleman talked about inverse kinematics. Inverse kinematics of a robot, for a particular robot, you have 8 different poses, 8 different solutions for same Cartesian pose, right? So which one do you choose, right? And most of the inverse kinematics, for many robots, only give you 1 because you use a Jacobian kind of least square type approach instead of finding the closed form. And some robots doesn't even have closed form solution. If anybody look at the Yumi, the ABB Yumi 7 degree freedom arm, fix one of the joint, you have 65, but you can still, so there's no closed form, you can still compute efficiently for all solutions. I'll mention that a little bit. So all of this, we lump on the bucket called redundancy resolution. That means you have multiple choices, right? So you have to resolve that redundancy. Okay, the next is to choose the waypoints. So for the robot program, you use waypoints and then you blend them together. So you also need to choose the motion segments, right? The motion primitive. Do you use linear motion, move L, Cartesian linear motion, or move C, Cartesian circular motion, or move J, that's the joint motion, straight line joint motion, okay? Of course, you have the corresponding interpolation of the position of the orientation. You also need to choose a blending zone, right? Different robots do blending differently, and they specify differently. They're different algorithms, and they don't tell you exactly what those algorithms are either. Okay, you just kind of draw a diagram, draw a curve. Yeah, secret sauce, right? And none of them work very well, and they all have their drawbacks. So, but you don't know. You have to find out. And then to choose the path speed, you get to choose those. All of this are motion programming. So basically, you need to do both, okay? So you can see that usually what's done is that you choose a uniform set of move L segments, linear segments, just like a CNC. The thinking is still very much CNC driven, not realizing the constraint of articulating a robot, okay? And then you have a mixture of L, C, and J, and you have the blending zone. So how's it done today? So how's it done today is that you put the part in the middle. Okay, so there's an intuition, arms should not be near singularity. So when it's outstretched, it's near singularity, it's near here, it's singularity, no good. Okay, somewhere in the middle. Okay, not systematic, but somewhere in the middle. And the tool orientation to just stay away from singularity stack. And then uniform space, straight line, that's how RoboTK does it, RoboMaster, Octopus. You can tweak those, but the tweaking is pretty much based on singularity avoidance. And then typically try to maximize the blending zone. The problem with the maximum blending zone is that you have tracking error. Okay, you have more smooth motion, but you have tracking error. And then you keep on lowering the speed until your stack is achieved. So usually that means you compromise on your performance if the speed is your cycle time is your performance. Now, for the dual arm case, it's even tougher. So how do they do it? Heuristically assign a percentage of motion. So you say, okay, I have a big arm, 60% goes to the big arm, 40% to the little arm. And then you use a single arm approach, right? All right, so you say, this can't be right? There gotta be room for improvement. And yet when we talk to people, everybody say, oh, soft problem. Okay, so, this is a Mac versus PC issue. So now you can see, okay, I use a Mac, so this, but you can see this is how the baseline, is done today. So we use the following approach. Basically, we decompose the problem. If you look at this as a gigantic optimization problem, forget it. It's not solvable. Obviously, NP complete. Just take forever. It's not practical. So we decompose the problem in the following way. First of all, we do post optimization and redundancy resolution to just tackle the redundancy resolution. Once you do the redundancy resolution, then instead of using uniform points, we use a greedy search. Basically, we want to use the least number of points to meet the kinematic fit. Okay, so we use J, C, and L. Okay, and then minimize number of waypoints. Why? Because the waypoints have blending. Blending screws you up, right? Compromise performance. And then we adjust the blending zone for uniform speed. Finally, the most important thing is what you specify, which we just talked about a little earlier that Matt was talking about when we were over in that corner, is that what you specify is not what you get, right? So for you say, I want to follow this path. I specify all of this waypoints with this blending zone. You don't know what the hell you're going to be getting, right? You may get close and you may get a blip. Every robot company does things differently, right? We use ABB, Motorman, and Fanuc, and even Universal, Sawyer, they all do things differently, and they don't tell you exactly how that's done. You can't even predict unless you run it, right? So what we do is use an iterative algorithm. First of all, we iterate in simulation. Now, and then port to physical robot, of course, you will operate differently. And then we train some more using the physical data, okay, iterate some more. Okay, so I'll talk about each one very quickly. So post-optimization, the redundancy resolution. So first of all, we use the standard. So earlier I was talking to somebody about Tony Matrowski. Is a redundancy resolution, standard stuff. Okay, local redundancy resolution using quadratic programming. But the challenge here is what is the acceleration constraint? This is where robots are different than CNC. Because the robots have articulated, so the constraints are post-dependent. The Cartesian constraint is dependent, how that relates to joint constraint, and the joint acceleration constraint depend on the Jacobian. But we don't know what the acceleration constraint. You look at the robot spec, you can of course see the joint velocity constraint, but nobody will tell you joint acceleration constraint because that's fundamentally the torque constraint, and then it depends on the inertia, depends on the load. You don't know what it is, right? You can't calculate it. So what do is that you have to shake the robot around, okay? Shake the robot around until you get a graph of experimental joint acceleration constraint. And it's not as bad as it sounds because it's essentially the shoulder joint and the elbow joint, which is Q2 and Q3. But but Q1, which is the acceleration, actually depends on the constraint. So this is experimentally obtained, and then we use so that's for a given pose, and then we optimize the pose based on that redundancy resolution algorithm. And we use differential evolution. I think somebody mentioned differential evolution earlier. And we use a standard open source differential evolution algorithm. And it seems to work reasonably well. And then we have the optimized pose, which is different than the intuitive industry practice post. Okay. The next is greedy fitting, which is straightforward, and then we get a sparse set of waypoints. And the third is blending zone. We usually have the largest blending zone, and then so we keep on increasing blending zone until you get some speed uniformity, and then we actually specify different speed in different motion segment. And finally, we do the iterative waypoint adjustment. And this waypoint adjustment is, basically you have all these waypoints, and you adjust these waypoints using a very simple gradient algorithm. And we use numerical gradient using simulation. But since we don't know the vendor-specific blending algorithm, we just use a standard cubic fit, okay, the cubic spline fit. And it turns out that fit, of course, it's not exact, but it gives you good enough gradient algorithm. And that's I was talking to somebody. You need a perfect model for inverse inverse problem for inverse kinematics and stuff like that. But you don't need a perfect model for gradient, right? Because that just gives you a descent direction. Even you're a little wrong, but you're still in the general descent direction. And then we use that to generate gradient, but we only do the gradient at the peaks of the error, and we'll only do the gradient near the waypoint, the waypoints near the peak. So an alternative method is to use reinforcement learning. Eugene mentioned reinforcement learning, and we applied that, and it gives a very intuitive kind of strategy, which is to adjust the waypoint in the error direction, versus where you want to be, the actual trajectory, the actual path versus what you actually have. So we basically combine these two, first of all in simulation, and then for the physical robot, and then adjust the waypoint until the performance met. So how do you evaluate performance? So Adam, we were talking about that earlier. So we basically consult our GE partner and say, what will convince you to be that this algorithm is useful? First of all, they say we can have a toy case which is challenging, where you have a lot of motion on a curved surface, and the normal goes back and forth. Okay, that's curve one. Curve two is a representative fan blade, kind of this curvilinear, thing that they gave us. And we try on the physical test bed, both simulation and physical tests on ABB robots and Fanuc robots. So Fanuc is over at their test site, ABB is our site. Again, we use RoboStudio and RoboGuide. The motion, so these are just waypoints. So we will do the algorithm in Python, and then we automatically ship it off, and that's the interface we built. John Watson built to automatically generate rapid code or Carol code that you will execute automatically. So you have everything will be everything will be automated, just like that. The performance, as I said before, that's what we want to do. So the performance we pose as this: you want to maximize the path speed subject to minimize cycle time, subject to the speed uniformity constraint, accuracy constraint, position, and orientation. Those are constraints. The one number you want to minimize is one number you want to maximize is a speed. Okay. So this is the a video. So we use Tesseract for visualization, for collision checking, etc. Okay, you do need to worry about collision as well, because you don't want to get too close, so you want to, so even for the initial placement. So this will, so we can, our workflow involve initial visualization, starting from the CSV file of the path, uniformity space, dense set of points. And this is our experiment. And then we will perform, the actual motion is very quick. So most of the time it's actually going to the starting point. And this is, and that's up, right? So, and then you can see the performance. So this is already 9th iteration. So you can see that's already pretty close to under below the 0.5. I should stop here. Okay. Okay. So you can see this is 0.5 is here, and then this is the speed, uniformity, and this is the orientation. And then you will do one more iteration, and then we'll stop, and then save the result. And so all this result, earlier we talked about benchmarking, and all of this are saved, in something like ROS-I, right? But how much do you save? This is a lot of data, right? But you need all of this data to show. Okay, so so this is just to show that from the first iteration to the last iteration, you can see the algorithm push all the peaks down. You can see the peaks, push it down while still remain speed uniformity. Okay, so this is after a lot of the testing with the ABB and FANUC. So for ABB, since we had the test spec, so we did a lot of testing. So the baseline is 0.1 meter per second. Okay, that's the best that can be done. That will still satisfy the constraint. So suppose you just use single arm, but you just optimize the waypoints. Okay, and to modify the waypoint, you can already double. Now, if you optimize the location, the pose, then you can even increase that some more. Now, for dual arm, you can actually increase by 4 times. So you say, okay, 2 arm, that's a lot of investment. But even for single arm, optimize the location of the arm and pose the arm makes a big difference. For curve 2, similar kind of result. For FANUC, I don't have the dual arm yet, so it's double for the curve 2. So FANUC, the geometry is a little different, but you can apply essentially the same algorithm. So the overall workflow is just 4 steps, right? I can't even read this; it's too small. But basically, you do you start off the curve in CSV file. You do the redundancy resolution, you do the motion optimization, and you do the waypoint adjustment. That's it. And then it's pausing. I don't know why it's pausing. Okay, so all the Python modules are available. There are different modules, and we use Tesseract for browser visualization, collision checking, not for past generation. And then we also develop Python wrapper. So to install a Tesseract and to be able to use Tesseract in Python, it's a simple 1-step. It's a Python wheel, very simple installation now. And basically, this is a very crude user interface that we have. Basically, it's 3 parts. You load the file, do the initial redundant resolution. The middle part is for the motion optimization. The final part, simulation and the runtime. Okay, so in summary, so we generate all of this stuff. I want to say the core one thing the industry can really improve a robot vendor, looking at you, Roger, is the coordinated dual arm. The dual arm coordination that's sold actually as a separate thing by different vendors are just terrible. Actually, the streaming like Multiplus, EGN, streaming motion, etc. They don't work for dual arm, and so you have to sort of artificially sync them up. So we have now since do some extension directly motion capture, directly to measurement. Also, we extending to a wire arc. So I talked to a number of you about our WEM cell. Okay, the Kodak problem. So you build something like this. And there are other issues, inverse kinematics. So for optimization, we need to find all solutions. So people would say IK-fast. Set a new algorithm that can outperform. And 7DoF arm, how do you parameter redundant degree of freedom? How do you do with singularity? And you can see the choice of singularity makes a difference. Of course, this is a KUKA arm. Is it KUKA or Sawyer? Iwa. That's right. Yeah, this is a KUKA. So you can 7DoF choosing the additional degree of freedom makes a big difference. And now David Coleman talked about in-space service essentially. Yes, 7DoF is big deal, but flexibility is very challenging, and that's up and coming. So thanks to ARM and thanks to the partners, and all the stuff is available on the ARM GitHub. I think there's a link early on. And of course, I didn't do any work. Everything is done by the partners. Thank you.
Time for one question for Dr. Wen. There is actually a repo that has the redundancy resolution piece working like a professor at a high school.
So that is outside of the ARM GitHub.
Questions for Dr. Wen?
Like a PhD in industrial robot programming.
Question for the speaker, has any of this been published in papers? I guess you can answer that question.
One paper is coming next week in ECRA. That's for single arm. Okay, so dual arm is under preparation. And there are two papers that are on the archive. One's the inverse kinematics, the other is a 7-DOF arm parameterization. Rather than using SEW, you can use a modified SEW. Yeah.
You go back to the improvements in speed that we were discussing.
Yeah.
So to a GE, you are at 396 millimeters per second.
Right.
Is it worth that going 451 by the capital?
Well, they already are. They are definitely go with dual arm. But they are having a heck of a time tuning them, and that's why we had this project. So now, so earlier we were talking about how do we transition a university-based research to industry research, right? So this is about TRL 6. Because we do, in the lab and, et cetera. So basically, we work with Boeing and other. They basically take this indoor and then they say, okay, get the hell out, right? Because we will absorb it. We will ask you questions, when we have any, but that's how they will go about doing it.
Excellent. Thank you, Dr. Wen.
Thank you.